Well, hello everybody. I hope that you guys are doing well. So the last class, which was before spring break and before the exam, we left off by covering chapter 16 from slide 1 to slide 26, where we introduced the concept of acid-base equilibria. Today, I'd like to do a short review of the material that we already covered and be able to continue from slide 27 on. So you might recall that we introduced the concept of Bronsted-Lowry acids and bases, which were proton donors and proton acceptors. And in this case, we're talking about a proton being a hydrogen ion or H+. Remember that the acid is going to be a substance that has a labile proton that can be donated, that is loosely bound to the molecule, and then a base is going to be a substance that is able to accept or bind to this proton, and therefore it has to have a lone pair of electrons available to be able to bind a proton. We introduced the concept of acid-base pair conjugates. And for example, here we have nitric acid versus the nitrite ion. The difference between these two is that the acid is going to be the substance that has an extra hydrogen ion, while its conjugate base has already donated that hydrogen ion. And so what is left is just the nitrite ion. Similarly, water and the hydronium ion are going to be acid-base pairs, where the hydronium ion contains an extra hydrogen ion relative to the water, right? Similar here, we have ammonia, which is going to be the base relative to the ammonium ion, which is its conjugate acid. So when you go from a base to a conjugate acid, what happens is that the substance gains a hydrogen ion or an H+, while if you're starting with an acid, the conjugate base of that acid is going to be the substance after you have removed a hydrogen ion from it. Remember that the hydrogen ion contains a positive charge, so if you're starting with a neutral compound, then the conjugate is going to be negatively charged. On the other hand, if you're starting with, let's say, a positively charged acid, once it has donated that H+, you would end up with a neutral molecule. We talked about the fact that the stronger a weak acid or base is, the weaker its conjugate is going to be, right? Similarly, the weaker a weak acid or weak base is, the stronger its conjugate base will be, or conjugate acid will be, I should say. We also touched on this table that contains a summary or a list of acids on the left and their conjugate bases on the right-hand side, and is organized according to strength. On the very top, we have the strong acids, followed by the hydronium ion, which is a fairly strong acid because, as you know, water doesn't want to have that extra hydrogen ion. It would rather be in its neutral form, so it wants to donate a proton. Under the hydronium ion, we have all of our weak acids, which include some of the ones that you recognize, such as acetic acid, phosphoric acid, hydrofluoric acid, but it also contains some conjugates of the strong acids, such as the hydrogen sulfate ion, for example. And it contains some other ions, such as the ammonium ion, which are substances that are able to donate protons. Underneath all of those weak acids, we have water. And basically water, as you can see, is a very weak acid. It does not really want to donate protons. It would rather stay in its neutral form. When we go to the right-hand side, that side is organized in the opposite direction, where the strong bases are at the bottom. And as we go out, we have negligible basicity, basically less basicity, less basic behavior. As we had said in the previous slide, the stronger the acid, the weaker its conjugate base. And similarly, the stronger the bases here, the weaker their conjugate acids are going to be. Just to remind you again, here we have the weak bases in the middle, and water is going to be an even weaker base than all of those weak bases. The reason for that, again, is that water would rather stay in its neutral form as is, as opposed to gaining a proton. When it gains a proton, it would become the hydronium ion, which is not the normal form for water, if you would. Similarly, below all of these weak bases, we have the hydroxide ion. So hydroxide ion correspond to a fairly strong base. All right, so from here we begin the new material. The first thing that we're going to talk about is the autoionization of water. Autoionization, as the name implies, is basically the transfer of a proton from one molecule to another of the same substance. For the case of water, let's say that we have two molecules of water. One of those water molecules, let's say this one, is going to be donating a proton. In this particular case, here is our proton that is being donated, and it's going to be accepted by the other water molecule that is next to it. That water molecule takes in that hydrogen, becoming now the hydronium ion, and what we are left with is the hydroxide ion in this particular case, right? So again, we have just two water molecules that are interacting in water. One of them ionizes by donating a proton, and thereby it is going to ionize the other water molecule by forming the hydronium ion. That can be written as is represented here in this equation, where we have two water molecules generating a hydronium ion and a hydroxide ion, and notice that this is an equilibrium process. Similarly, we can kind of simplify this equation by showing what happens to one water molecule. So one water molecule is going to dissociate or ionize into hydrogen ions and hydroxide ions. And you might remember that I mentioned last class that for chemists, we typically represent the hydrogen ion or the hydronium ion as being the same, because we understand that the hydrogen ion in solution is really not going to stay like this. In reality, it will actually come and react with another water molecule in order to form the hydronium ion. So what I want you guys to be able to do is to look at these two equations and be comfortable with the fact that they're both showing the same process. All right, if we go to the next slide, right here we have the same two equations written. So here we have the two water molecules autoionizing, and then on the bottom we have just one water molecule which is ionizing by generating the hydrogen ion and the hydroxide ion. We can write the equilibrium constant expression for both of those. Remember that the equilibrium constant expression is your capital K, and that K is going to be your products over your reactants, as we always do. Notice that in these particular cases, the reactants are both pure liquids, and thereby they're not going to be included in the equilibrium expression, right? So all that we're going to have is our products. So for the first equation, our K, our equilibrium constant equation, is simply going to be the multiplication of the concentrations of the two products, which are the hydronium ion and the hydroxide ion. And similarly, I could say that the equilibrium constant expression for the second equation is simply going to be the multiplication of the hydrogen ion concentration times that of the hydroxide ion concentration. Since I said that both of these processes or both of these equations are really showing the same process, those two are actually identical. And notice that I have called it Kw in this case, where the W basically indicates that we're talking about the dissociation or ionization constant for water, right? So Kw is going to be the equilibrium constant basically for the dissociation or ionization of water. And notice that that Kw has a value of 1.0 times 10 to the minus 14 at the temperature of 25 degrees Celsius. This is a number that I actually do want you to memorize. That number is going to be important. You will be using it a lot in this chapter. Again, notice that this is at 25 degrees Celsius. Remember that the value of the equilibrium constant is temperature dependent, and so we need to be careful to make sure that we are working at 25 degrees Celsius. Now, if in a problem, if I don't mention a temperature, or if I don't provide you with a different Kw, it is safe for you to assume that we are working at 25 degrees Celsius. Now notice that that Kw is very, very small, 10 to the minus 14. That low value indicates that the reactants are favored, right? Most of the molecules are going to stay actually in the neutral form, in the molecular form of water, because as we mentioned before, water would rather really stay in the neutral form as opposed to being in the hydronium ion form or in the hydroxide ion form. The other thing that we want to remember is that K's in general, your equilibrium constant expressions, including Kw, increases with temperature. And so if you have a problem where the temperature has been changed, you want to make sure to adapt to the situation. In most problems, you either will be provided the concentration information to be able to find W, or you will be provided with the value of Kw for that particular problem. All right, so this slide contains some very important information that I want you to remember. And this is that by definition, a neutral solution is one where the hydrogen ion concentration is equal to the hydroxide ion concentration. That is the definition of a neutral solution. This is very important for you to remember, okay? In an acidic solution, on the other hand, the hydrogen ion concentration is going to be greater than the hydroxide ion concentration. That means that we have more of that hydrogen ion concentration than we do of the hydroxide. Finally, in a basic solution, basically the opposite happens, where now your hydroxide ion concentration is going to be present in higher concentration than the hydrogen ion concentration, okay? I need you guys to remember these definitions so that you're able to answer some questions. In all cases, however, regardless of what the value of those concentrations are, the multiplication of those two will always be equal to Kw. What that means is that if you remember this equation, which you should, you would be able to find the concentration of the hydrogen ion concentration, for example, if you have the hydroxide ion concentration. Or the opposite, if you have the hydrogen ion concentration, you would be able to find the hydroxide ion concentration. Of course, you're going to have to adapt the equation to be able to solve for what you need. For example, if I want to solve for the hydrogen ion concentration, I would find that by taking my Kw and dividing it by the hydroxide ion concentration. Similarly, if I needed to find the hydroxide ion concentration, I would do it by taking my Kw and dividing it by the hydrogen ion concentration, right? It's just simple algebra, but you do need to remember this equation to be able to do that. The equation will not be provided to you, and of course that equation basically comes from your equilibrium constant expression by just looking at the products of the dissociation. Now, this, meaning this relationship of Kw being equal to hydrogen ion and hydroxide ion, and these definitions above, are regardless of the temperature. So even if we have a different temperature, let's say 50 degrees Celsius, all of this would still be true. And so if I have the value of Kw at that temperature, then I would be able to substitute in these equations and be able to find the concentrations of hydrogen ion and hydroxide ion at that particular temperature. Again, remember that with different temperatures, the Kw value is different, changes. All right. So first example, calculate the concentration of hydroxide ions in a solution that contains a hydrogen ion concentration of 4 times 10 to the minus 6, assuming that the temperature is 25 degrees Celsius. All right, so to do this, we're going to use the equation that we just had. It said that Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. In this particular case, we have the hydrogen ion concentration, and we know that we are working at 25 degrees Celsius, therefore we know the value of the Kw. All that we have to do is to solve for the hydroxide ion concentration, which is going to be equal to Kw divided by the hydrogen ion concentration, and that's equal to 1.0 times 10 to the minus 14, that's my Kw, divided by the hydrogen ion concentration, which is 4.0 times 10 to the minus 6. That is going to give us a value of 2.5 times 10 to the minus 9. And the units of that is going to be molarity. All right, simple enough. All right, the next thing, or the next question in this case, is what is the hydrogen ion concentration in a neutral solution at 25 degrees Celsius? All right, so we're still going to start with the same equation. Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. And we know that at this particular temperature, this has a value of 1 times 10 to the minus 14. If we had a different temperature, which by the way you're going to have in your homework, then you would replace the Kw value with whatever value is appropriate for that temperature. The next thing that we're going to do is that we know that this is a neutral solution, and in a neutral solution we know that the hydrogen ion concentration is equal to the hydroxide ion concentration, because that is by definition. And so in this case I can go ahead and call each of those X. Both the hydrogen ion concentration and the hydroxide ion concentration are being called X. That's just basically what I want to solve for. So what I did is that I came back here and I replaced my hydrogen ion concentration with an X, my hydroxide ion concentration with an X. When I multiply those two together, I get X squared. So X squared is equal to 1 times 10 to the minus 14. I can then solve for X by taking the square root of both sides, and that gives me my answer to the problem. Again, you're going to have a homework problem that's something like this, but maybe at a different temperature. So hopefully this will get you on the way to being able to solve that easily. All right, and so after we have solved this, this is actually an important information for us to have. So in pure water at 25 degrees Celsius, the hydrogen ion concentration and the hydroxide ion concentration is equal to 1 times 10 to the minus 7. This is something that is pretty important for us to remember. Remember that in a neutral solution, both of these are equal. In an acidic solution, on the other hand, the hydrogen ion concentration would be greater than 1 times 10 to the minus 7 molar at 25 degrees Celsius, while in a basic solution, the hydroxide ion concentration would have been greater. It would have been greater than 1 times 10 to the minus 7 molar at that temperature. All right. The next thing that we need to talk about is the relationships. And this is something that it's another important slide conceptually that I want you to remember and to understand. So we said that in neutral solutions, the hydrogen ion concentration is equal to the hydroxide ion concentration. In pure water, according to the previous problem, the concentration of these two is going to be equal to 1 times 10 to the minus 7, right? This is only at this temperature. In an acidic solution, we know that by definition, the hydrogen ion concentration is greater, which means that it is going to be greater than 1 times 10 to the minus 7. That means also that the hydroxide ion concentration must therefore be less than 1.0 times 10 to the minus 7 molar. Finally, in a basic solution, the hydrogen ion concentration is going to be less than the hydroxide ion concentration because the hydroxide ion concentration is going to be bigger. So therefore, the hydrogen ion concentration will be less than 1 times 10 to the minus 7, and therefore the hydroxide ion concentration would be greater than 1.0 times 10 to the minus 7. The reason for this is that the product of the two will always be equal to Kw. So again, if we know the value of one of those two, either the hydrogen ion or the hydroxide ion concentration, we are able to solve for the value of the other using this equation. All right, the last problem before we move on to the next topic is what is the concentration of hydronium ion in a solution that has a concentration of hydroxide that is equal to 8.9 times 10 to the minus 9 molar. All right, hopefully you guys are going to pause and actually do this yourselves, but I'm going to go ahead and get started. So the first thing is that, okay, we have a hydroxide ion concentration. What they're asking us for is the hydronium ion concentration. And what you needed to remember is that for chemists, the hydronium ion concentration is basically equivalent to the hydrogen ion. And so what I'm really asking is for the concentration of the hydrogen ions in solution. Of course, to be able to solve for this, we have our equation of Kw is equal to H plus hydroxide ion concentration. In this particular case, we're going to solve for the H plus, which is what we're looking for, and that's going to be equal to Kw divided by the hydroxide ion concentration. That is equal to, actually, what temperature are we working at? So since we don't say, that means that we are working at 25 degrees Celsius. Therefore, what I can say is that this is going to be equal to 1.0 times 10 to the minus 14 divided by hydroxide ion concentration, which is 8.9 times 10 to the minus 9 molar. And therefore, my hydrogen ion concentration is going to be 1.1 times 10 to the minus 6. And we are done. All right, guys, see you on the next video.